In the last section, we looked at the the corresponding angle similarity theorem. And this had that, well, if we had two angles that were congruent, then we could say that two triangles were similar. In this section, we're going to look at two more, SSS and SAS, which are very similar, but the thing to remember is that these show similarity. They do not show congruence. So what this first one says is, if you have two triangles that follow corresponding side lengths that are proportional. So the ratio of AB and RS is the same as AC to RT and BC to ST. So I've got this set up here. AB over RS is equal to, basically they all have the same common scale factor. If this is true, then you have that these two triangles are similar because they follow the same proportion. In the second theorem, the side angle side similarity theorem, again this will not show congruence, but it will show similar, meaning one triangle is smaller or just zoomed in, blown up version of the other one. And what this requires is that you have an angle, so here we have angle X and angle M, that are congruent. And you must have two sides that are proportional. So in this case we have ZX is proportional to PM, and XY proportional to MN. They must follow that same scale factor. In these examples, we are going to justify whether or not we can say that these triangles are similar. So in number one, what I notice is that, first off, we don't have any angles. So I'm going to steer clear from side angle side and angle angle. I'm probably thinking, well, if I can prove by side that these are similar, then I should be good to go. So what is required of side is proportional sides. I'll start with 15 divided by 45. Reducing that fraction, so that's the fraction 15 over 45. Reducing that, we get 1/3. Now this should be true that I have a scale factor of 1/3 for all of these sides when I set up the proportion. Next one, we have 7 divided by 21, which is equal to, when I reduce it, 1/3. So I'm seeing a common scale factor. And lastly, 10 divided by 30 is equal to 1/3. So I have the common scale factor in all three, which means that yes, these two triangles are similar by side. One thing to point out is that notice how these triangles are drawn on the paper, but how I matched up 7 with 21 and 10 with 30, rather than 7 with 30. If I had done that, the common scale factor would not have worked out. So you get to choose how you'd like to orient these triangles to see if they're somehow similar. But now when I go to make my similarity statement, I'm going to start with triangle RPQ. But now I have to make sure that that's oriented in the same way the second triangle is. So what I can say is triangle OMN. Since M matches up with P, R matches up with O, R and O, they're just kind of reversed around, and then Q and N match up. Number 2, I see two angle measures given in each triangle. And I don't have any lengths, so I should be thinking right off the bat, I have to somehow show this using AA, the angle-angle similarity theorem. So let's fill out the rest of the angles. Well, if I have 120 and 20 degrees in the larger triangle, to find the third angle, I just have to know that all of these sums of the angles add up to 180 degrees. So 40 plus 120 plus 20 is 180 degrees. I can fill it out. Lastly, this smaller triangle, I can find that this angle here is 20. So you'll notice that all of the angle measures match up. So yes, these two triangles are similar, and I can make my statement. Triangle QPR is similar to triangle, make sure you match everything up, NOM. In number 3, I see I have a side, an angle, and a side. So I should be thinking right off the bat SAS to prove that these two triangles are somehow similar. I can set up my ratios. So I've got 9 over 3, which is equal to, simplifying that, 9 and 3 have common factors of 3, so this is the same as 3 over 1. That's my scale factor. 15 divided by 5, again, larger over smaller in this case, I got to keep that together, is equal to, 5 is a common factor, so 5 goes into 15 3 times, 5 goes into 5 1 times, 3 over 1. They both have the common scale factor, which means we have two sides that are proportional, an angle that is congruent, so we can say that yes, these two triangles are similar by side angle side, and we can make our statement, triangle ABC is similar to triangle JKL, making sure to match up the vertices. In number 4, I see parallel lines. Whenever I see parallel lines, I like to extend them for a visual, which means that I have some transversals here. So parallel lines should automatically be a cue that lets you know that corresponding angles are going to be found. And we know that corresponding angles are congruent. So on this first one, we have a transversal and two parallel lines. So what we can say is this angle here and this angle here are both congruent by corresponding angles. So I'm going to mark that down, congruent. Similarly, angle E and angle D are also congruent by corresponding angles. So now what I have is, in the smaller triangle, DBC, we have two angles congruent to the larger triangle, EAC. So by angle, we can say that yes, these are similar. Triangle AEC, that's the larger triangle, is similar to triangle BDC. I want you to now try number 5 on your own. If you have to pause the video at this point to try it out, that's fine, but I'm going to move on. In this example, we're told to verify that these two triangles are similar. So let's go ahead and draw the triangles. It does not matter what they look like. They can be equilateral, isosceles. It's just a general representation. It's not going to be accurate, but the important thing is that you label everything correctly. So we have triangle ABC and triangle D, E, and F. I've drawn them oriented the same way, so it's easy for me to match things up. We're given AB is 12, the side length, BC 15, and AC is 9. EF is 10, FD is 6, and DE is 8. Now that I have it all drawn out, notice it's not to scale, but that's okay because the numbers is what matters. So what I can do is find the ratio between all of them. First thing I'll do is I'll take the ratio of AB to DE, and that's equal to 12 over 8. So I'm going to write 12 over 8. Simplified, well, 4 goes into 12 3 times, and 4 goes into 8 2 times. My scale factor is 3/2. Now, if that's true for all of the other sides, I'm good to go. So let's try it. 15, this is side BC, divided by 10, that's side EF, is equal to, well, 5 goes into 15 3 times, 5 goes into 10 twice, 3/2. Same scale factor, we're on the right path. Lastly, 9 over 6. That is equal to, 3 goes into 9 3 times, 3 goes into 6 twice, scale factor of 3/2. All three have the same scale factor, which means that we have 3 proportional sides. So yes, these two triangles are similar by side, side, side. Another example of checking whether two triangles are similar or not. I have two sides and an angle, so I should be thinking, well, let's prove these are similar by side, angle, side. So the first thing we need is, well, we have it. We have two congruent angles. Angle S must be congruent to angle Y, because all 90-degree angles are congruent to all 90-degree angles. Now we have to find the scale factor for the sides. So I'm going to start with 4 and 6. 4 divided by 6 is equal to, reducing this to thirds, since 2 goes into 4 twice, and 2 goes into 6 3 times. Scale factor of 2/3. Now let's see if that matches up with the other side. So we can take 6 divided by 9, which is the same as 3 goes into 6 2 times. 3 goes into 9 3 times. So again, we end up with 2/3. So what we have is a congruent side and congruent angles and 2 proportional sides, which means by side, angle, side, we can make our similarity statement. So triangle RST is similar to triangle XYZ, making sure to match up the vertices. Alright, let's tackle some proofs. First thing we got to look at is, what is this question asking? And it wants us to prove that ILS is similar to ERS, triangle ERS. Certainly they look similar, but it's our job to actually show this. So we'll start with what we're given. And we're given that IR and EL are altitudes of these triangles. So I'm going to write that down as the given. Altitudes, IR and EL. And that was given. We should have an end goal in mind, and the end goal is to prove triangle similarity. So I might as well write that down now. Triangle ILS is similar to triangle ERS. That's what we got to get to. In step 2, the reason is already given for us. It says definition of an altitude. Well, let's think way back to altitudes. Chapter 5, what did an altitude of a triangle tell us? Well, what an altitude was you take a vertex and you drop a perpendicular down to the opposite side, which means that IR intersects PE at a right angle. So what this tells me is that angle 2 and angle 6 are right angles because of these altitudes. So I can say this is a right angle and this is a right angle. Which would also tell me that angle 1 and angle 5 are right angles, but that's not part of the triangles we're trying to prove similar, so I really don't care. So what I'm going to say here is that angle 2 and angle 6 are right angles. Step 3, angle 2 is congruent to angle 6. Well, yeah, that makes sense. It's kind of a duh statement, because all right triangles are congruent. Or, excuse me, all right angles, rather, are congruent. Step 4, the reason's already given for us. Vertical angles are congruent. Well, where I see vertical angles are angles 3 and 4, because they're crossing lines and they're opposite sides of the intersecting lines. So we have that angle 3 is congruent to angle 4. So why did we do all of that? Well, now what we have is an angle congruent to an angle and an angle congruent to an angle of two triangles. That's all we needed to prove that these two triangles were similar. So step 5, we can state that they're similar by the angle-angle similarity postulate. In this last example, we need to prove that triangle ABC, that's the larger triangle, is similar to ADB, the smaller triangle. So what we can look at is, well, we've got some kind of angle given. I see no side lengths though. So we're probably going to use angle-angle or perhaps maybe side-angle-side to somehow show this. Step 1, write it down. It's your given. That should be the easy points. As well as your end game, in step 5, we can state already that those triangles must be similar. That's what we're looking to get to. So the first thing we're given is that BD is perpendicular to AC. And AB is perpendicular to BC. Now in this picture they've already drawn the right triangles, or the right angles. But in step 2, we have to show that. So we make a statement that angle ABC and angle BDA are right angles. Which makes sense because perpendicular lines always form right angles. And we've already wrote them on the diagram. We just had to show that. Step 2, we can say that the angles are congruent. Why? Well, this is kind of another duh statement because all right angles are always congruent. All right angles are congruent. So, next thing I have is, well, let's see. We have shown that one pair of angles are congruent. We have to somehow come up with another. But notice here, if we look at the bigger triangle, one of the angles here is angle A. The smaller triangle, one of the angles is angle A. So angle A is congruent to, well, itself, angle A. And that's by the reflexive property, which states that everything is congruent to itself. So now what we've got is two angles. Last step, these triangles are similar by angle-angle. In class, you'll be asked to show a couple of these, so be prepared if you need to go back at this point and revisit one of the 3 different proofs, whether it be the 2 that I did in this section or the last proof in the last section. Now would be a good time to look back at that.